Right, grade 12s, on to topic 4, which is very much related to topic 3. We're not actually going to learn anything new. It's just that these are more complicated double angle identity questions, all very much taken from exams and stuff, and so this is exactly the type of question that you could expect. So example 1, very, very common question. You will kind of recognize this idea from grade 11. So in grade 11, we often used to ask you questions like if cos of, and we'll give you a random angle, and we say it's equal to k, and then it'll say determine the following in terms of k without a calculator. Now we say without a calculator, otherwise you could kind of figure some stuff out using your calculator the whole time by figuring out what k actually equals to. And now that's not the point here. So what this means is that every single one of these questions have to somehow be reduced to something involving cos 25. So some of these will be things that you remember from last year. So going back to a grade 11 type example, if they ask cos 155, my first question is there a way to rewrite 155 using 25? And my first guess is using 25 and an axis, because then I can use reduction. And so this is exactly that type of example. You can rewrite 155 as 180 minus 25. So that's in quadrant 2. So cos is negative, but my name stays the same. So it's negative cos 25, which is negative k. Now, you don't actually have to find out what k is. You're just expressing things in terms of k. Now, personally, you don't have to write down this second line. You're welcome to go straight to the reduction. I'm just writing it in because we're probably a little bit rusty on reduction for a while. Right, let's look at the next one, cos 50. Now, that one I would never have asked in grade 11, because the moment I see 50, I'm thinking, gosh, it's double 25. So now this is the complexity, is that you have compound angles at your disposal. It's fairly rare to use compound angles because compound angles are then so complicated in their identities. But double angles come in a lot. Now with cos especially, there's 3 versions of the double angle identity. Now which one would I use? Well, you've been given the fact that cos 25 is k. So it's far easier to write this as 2 cos squared 25 minus 1, rather than using the combo of sine and cos or using the sine squared one. So then don't forget that cos 25 is k. So this is 2k squared minus 1. So that's the first way a grade 12 question can look. Let's look at the next one, sine 25. Now, this is something we did do in grade 11. I can't rewrite 25 using 25 and try and magically change sine to cos. And so this is precisely an example of where drawing a right angle triangle using what you've given is very useful. Now, I often do this actually at the beginning of questions like this because inevitably you need the information we're going to find out. So if this was 25 degrees and this was a right angle triangle, you've been told that cos of 25 equals k. So as a fraction, that would be k over 1. Now, cos is adjacent over hypotenuse. So if this is 1, my adjacent would be k, and now I need to find out what my opposite is, and I'm going to use Pythagoras. So I don't want to write O because opposite O looks like 0, so let's just call this the y value. So if I say k squared plus y squared equals 1, Pythagoras. Now you don't actually ever have to show this working because you get so good at it that you just automatically know what it is. So y squared is 1 minus k squared, and then I would root. Now I don't have to worry about it being a positive or negative because this is 25 degrees, so it's a right angle triangle. Everything would be positive. So now I know that this is root 1 minus k squared. Now once you've done that right angle triangle, it means that you can work with any ratio of 25. You can do tan, you can do sine, and so in future I generally draw this triangle the moment I see one of these k or t or m type questions that they often ask. I also often work out this angle here because it means that I can do sine, cos and tan of that angle as well. So don't forget, if you've got 25 and 90, this one would have to be 65. Actually, yeah, no, that is right. Just checking. 90 minus 25 is 65. Right. So that means that I could do sine, cos, and tan of 65 as well if I wanted to. So now I can look at sine of 25. If you were thinking of a right-angled triangle, it would be opposite over hypotenuse. Now I'm not going to bother writing over 1 because dividing by 1 doesn't matter. So I get root 1 minus k squared. Now that helps me with sine of 50, because sine of 50, this is a double angle. But if I hadn't figured out what sine of 25 is, I wouldn't be able to do this, because this is 2 sine 25 times cos 25. I hope I said 25. Right, so this is 2, and this is root 1 minus k squared, and this is k. And you could combine the k into the root, but it really is not worth it, and it doesn't get any simpler. So that's the best it can get. Right, let's look at example 2, which is a very similar idea. So sine of 18 degrees equals t. Determine the following in terms of t without the use of a calculator. So you start to recognize these type of questions. So immediately, because I've seen that this comes up a lot, I would draw my triangle. I would write in 18 degrees, and I think that that makes this 72. Now it says sine. Now sine by definition is opposite over hypotenuse, and this will be t over 1. So this is t, this is 1, and then we start to get so good at this that we just write 1 minus t squared Pythagoras, because we've done it so many times before. So on to the question. This first question said cos of 18. Now it's actually really easy, because cos is adjacent over hypotenuse. So adjacent is root 1 minus t squared. I'm not going to bother writing divide by 1. Sine of 78. Well, I thought this could help me, but that's 72 in the triangle. So 78. So can you rewrite 78? And my first kind of thought is, can you use an axis and 18 degrees? Now, 90 minus 18 won't work, because that's 72, so that won't work. Can you do a double angle? Well, 78 is double 36, and that's not 18. And so my last kind of desperate attempt would be, can you use a compound angle? Now, if you're using a compound angle, you would have to be writing it with a special angle, because you can't possibly have another angle which you don't know anything about. And so fortunately I'm comforted here, because this is a special angle. So this is very rare that you use a compound angle, but not unheard of. So this is 60 degrees plus 18 degrees. So my compound angle identity is sine the first, cos the second, plus cos the first, sine the second. So sine of 60 is root 3 over 2, so it's root 3 over 2 times t, plus cos of 60 is a half, and this is root 1 minus t squared. Now, not that it makes it look any prettier, but I would probably just write this with one denominator. So it's root 3 times t plus root 1 minus t squared. So not a particularly pretty answer, but pretty nifty question. So note that my first port of call is to check, can I use an axis in 18 degrees? My second port of call is it a double angle? And then when I'm desperate, I say to myself, is it a compound angle? And hopefully then using a special angle, because otherwise I'd really struggle. Right, next one, sine 36. Now, I see 36, I think double 18. And if I checked an axis, it would be 90 minus, I think, 52. Well, 52's got nothing to do with what I'm talking about, so definitely double angle, quite useful here. So this is sine of double 18. So this changes this to 2 sine 18 cos 18. And I think sine 18 was the t. Yep, sine 18 was t. So this is 2t times root 1 minus t squared. Right, on to the next one. Oh, the moment I see 198, I immediately think, that's 180 plus 18. So there's been pretty much an example of every type of question they could give you here. Now, tan 180 plus, that's quadrant 3. Tan is positive. And so it's tan 18. And tan 18 is sine of 18 over cos of 18. Or instead of using that, I could actually go and look at my triangle. And so I could say, or I could say it's opposite over adjacent. And both of these times, sine 18 is t, and cos 18 is root 1 minus t squared. But if you go to your triangle, opposite is t. If I go up here, opposite is t, and adjacent is root 1 minus t squared. So I could actually use my triangle or the definition of tan there. Now, so this was a really good example because A was involving the triangle, B was involving compound angles, C was a double angle, and D was an axis. So it's pretty much the entire variety of ways they can ask these types of questions. Okay, on to example 3. Example 3 says, without the use of a calculator, simplify the following: cos 68 and then cos 34 minus sine 34. Now, 68 and 34, I'm hoping immediately you see those. You're like, oh my word, 68 is double 34, so that has to be some kind of connection. If you didn't see that, you kind of got to go through the motions. Can you rewrite 68, 90 minus what? 22? 22's got nothing to do with 34. So eventually, once you've looked at a couple of options, hopefully you get down to double angles. So cos of 68 over cos 34 minus sine 34 is equal to, this is cos double 34. Now the important question is going to be, which identity do I go with? Now, ultimately you want to simplify this, which means that denominator hopefully is going to somehow cancel with something, and your denominator is a mixture of cos and sine. So personally, I would pick the mixture identity at the top. So cos squared minus sine squared. Now you're going to hear me say that a lot, because when we go to equations and identities, I often say, let's look, should we choose the mixture, or should we choose just the one with cos or just the one with sine? And so here it made sense to do the mixture, and now this doesn't seem to want to simplify, except, don't forget, you can only ever simplify when it's one term over one term. And how do you make something one term? You factorize. Oh, that's not a 34. So you start to get really good at seeing this, but that top is a dots. So it's cos of 34 minus sine of 34, cos of 34 plus sine of 34 over cos of 34 minus sine of 34. And so these end up cancelling. And so this simplifies down to cos of 34 plus sine of 34. Now, if you have a look at this, can this get any simpler? Well, I have no identities that involve, adding cos and sine. And so I think that's as best as I can get if I'm not using a calculator. Now, mostly in exams, they tend to give you questions that kind of whittle down to something neat. This doesn't particularly whittle down to something neat. So if you're nervous, you just put the question in on your calculator and your answer in on your calculator and check that they do actually match. Right, on to example 4. Determine the value of sine 22.5 without a calculator. So can I write 22.5 as a compound angle? Probably a compound angle using two special angles would be useful. And if you play around a bit, you realize you can't. Now you start getting used to 22.5 because you start realizing that 2 times 22.5 is equal to 45. So 22.5 is a very commonly used angle. Now, sine of 45, I know a lot about. Sine of 45 is root 2 over 2. Now, sine of 45 would be equal to 2 sine 22,5 times cos 22.5. Now, the problem here is that I know nothing about cos 22.5. So I know sine of 45, and I'm trying to find the value of sine 22.5, but I also don't know cos of 22.5. And so the sine identity here isn't helping me because it's a combination of sine and cos. And I don't really want a combination right now because I'm trying to get sine of 22.5. So what identity does not involve a combination? That would be the cos identity. Cos, not 35, sorry, cos of 45 would be equal to, now I don't want to use the combo. So either I want to use 2 cos squared 22.5 minus 1 or 1 minus 2 sine squared 22.5. Now I hope it's pretty obvious that I'm trying to find out what sine of 22.5 is. So it would make sense for me to use this version of your cos double angle. Now, how do I know that? I know that because this is cos double 22.5. Oh, that definitely doesn't say 22.5. So personally, I probably would have jumped straight at the orange and thought, oh, sine of 45, cool. And the moment you write it down, you start to go, hang on, this is never going to work out. And so that's why I tried the cos double angle. So it's quite something really, really useful to remember is that cos double angles can actually get you an identity with only sine in it, which is quite useful. Now, cos 45 is root 2 over 2. And so basically this is like an equation. I'm now solving for sine of 22.5. Now, I said without a calculator, so I would personally, what I would do is take this term to this side and bring this term to that side. So I actually get 2 sine squared 22.5 is equal to 1 minus root 2 over 2. Now, surds come into this a bit, and don't be afraid to use your calculator a little bit. So I would divide everything by 2, so I get sine squared 22.5, and if that's divided by 2, and that's divided by 2, and now I would probably try and simplify this to one fraction. So let me LCD that. So this is multiplied by 2 to get an LCD of 4. So it actually becomes 2 minus root 2. And finally, I just have to square root that. So sine of 22.5, even though it doesn't look very pretty, is the square root of 2 minus root 2 over 4. Now, to make this look a little bit prettier, what I probably would do is separate, so square root the top and square root the bottom, because the square root of 4 is 2. So it doesn't look very nice, but again, pick up your calculator and go sine 22.5 and check what the answer is, and then check what your version, the surd version is, and check that they equal. Right, so example number 5. Sine 31 equals p. Express the following in terms of p. Oh gosh, we've seen this before. So let's draw our triangle just in case we need it. You start getting really good at this. This is 31. Now it says sine of 31 is p. So this would be opposite over hypotenuse would be p over 1. So this is p, this is 1, this is root 1 minus p squared because of Pythagoras. Now if I do some quick working out, I think this is 59 degrees, and that's 90. So what is sine of 329? Okay, well, can I rewrite 329 using 31? And my first check is, can I use an axis? And I think that works out perfectly. So this is quadrant 4. Sine is negative, but the name stays the same. So this is negative p. So that's your most common grade 11 type example. B is the perfect one for why we need the triangle, because cos of 31 is adjacent over hypotenuse. So because I've drawn the triangle, I can go straight to my answer. So we actually give you marks for the triangle, because that would be like a 3-mark question, simply because the triangle takes time. Right, cos of 62, you start to get really used to these, because cos of 62, that's cos of double 31. Now, I definitely would choose the one involving sine, because then I don't have to worry about any of these other horrible roots. So this is 1 minus 2 sine squared 31, and sine of 31, I think, was p. So it's 1 minus 2p squared. Now again, you could use the other versions, the cos squared 31 minus sine squared 31, and it actually will simplify down eventually to the next one. Right, cos of 91, gosh, that's never going to involve an axis and 31 degrees. Doesn't look like a double angle, and so when I'm desperate, I go to a compound angle. And this is indeed a compound angle, because it's 60 plus 31. So my compound angle identity says sine the first angle, cos the second, plus cos the first, sine the second. So sine of 60 is root 3 over 2. This is root 1 minus p squared, as far as I remember. Cos of 60 is a half, and 31 is p. So if you wanted to, you could write this as one denominator of 2. This would be plus p. You could put the 3 in, so you could multiply your surds together and get that if you wanted to. Right, so again, good question of showing you all the different options that they can ask you, but you'll notice that these start to become very predictable. So the great thing in Trig is the more you practice, definitely the better you get at it. Right, a couple more examples to go. Let's have a look at example 6. Prove that sine of 42 plus sine of 18 equals cos 12 without a calculator. Right, so I'm going to take my left-hand side and my right-hand side. So this is a little bit like an identity. My right-hand side is cos 12. Now, there's not much I can do with cos 12. So I'm guessing I need to start with this left-hand side, which is sine of 42 plus sine of 18. So my first thing is, how could I possibly write both of these angles, hopefully using 12? So how could I rewrite 42 using 12? Now my first guess would be an axis, but that's not going to work here. Second would be double angles. And lastly, because I'm desperate, I can write this as 30 plus 12. Okay, how can I rewrite 18? Again, I check axes, I check double angles, and eventually, I wrote plus 2. 30 minus 12. And so basically, this is going to be quite an interesting compound angle thing. So this is 30 plus 12, and this is 30 minus 12. So if I do a compound angle identity here, it's sine the first, cos the second, plus cos the first, sine the second. So that was the first one. If I just color coordinate it. Now this one is sine the first, cos the second, but it's minus cos the first, sine the second. Now hopefully there's some like terms here that can subtract away. So those are like terms, but I'm adding them, and so I'm going to get 2 of them so that I can add. And these, cos of 60, I don't know why I wrote 60, really. Sometimes I wonder. So let me erase that. This is not a 60, it's a 30. I was expecting there to be some like terms that cancel because these were the same angles. So that's how I picked that up. So those disappear. And if I actually just write down what those first two, sine of 30 is a half. So it's a half cos 12 plus another half cos 12 from here. And so a half plus a half is 1. Again, clearly too tired to do this. So this is cos 12. Now, you'll probably look at this and go, hang on, didn't we do this exact question in a previous lesson? And that's the thing. Eventually in Trig, all these questions kind of become versions of each other. And so you really do have such an advantage once you've practiced quite a lot. Right. Let's look at the next one. Determine the following without a calculator. Sine of 150. Now that's good, because immediately I know I can do reduction. So I probably wouldn't bother writing this line, but just so you know, I'm going to do that. Cos of 105, well, 105 would be 180 minus 75. Now, that's not a special angle. It would be 90 plus 15. That's not a special angle. But if I look right next door, there's sine of 75. So I'm starting to think, hang on, this could be useful. So even though I don't know where it's going, why don't I rewrite this cos as 180 minus 75, and then let me leave the sine of 75 alone, and then we'll see where it goes. So my first term, sine is positive in quadrant 2, so this is sine 30 degrees. Cos is negative, so this is actually negative, but my name stays the same, so 75 degrees, and then times sine 75. Now, you get really good at this, but the moment I see cos 75, sine 75, I think double angles, because the moment you have sine of an angle then cos of an angle, it is a double angle. Yes, the coefficient might not be right and the negative might not be right, but you can fix those. So let's just get rid of this negative sign to the front. So if I bring the fact that you're multiplying by negatives, this is negative. Sine 30 is a half, and then I've got this sine 75, cos 75, which I'm going to rewrite as a double angle. Now I'm going to rewrite it a double angle as long as I have a 2. So if I have 2 sine 75, cos 75, it's going to be a double angle. So I've added in a 2 there. Now you can't just add in a 2 like I've said in the previous video. That means you have to halve it as well, because a half times 2 would be 1, which is the actual coefficient there. So if you're going to add in a 2 because you want the 2 to be there, you also have to add in the half. Now, I had a half originally, so that still pops down. Then I have the half and the 2 to cancel each other out. So what actually ends up happening now is I have negative a half times a half, which is negative a quarter, and this is now a sine double angle. And so it's double 75, which is sine 150. Now that in itself is a reduction. So if I keep going, now I actually did sine 150 earlier, so I know that sine 150 is actually sine 30. I've done it up here. So I can kind of skip some steps a bit. Now sine 30 I know is a half, so I get a quarter times a half, and I get negative 1/8. And again, you can just pick up your calculator and you can tell if you're right, which is what's wonderful about Trig. So you do a quick check. If you're right, you move on. If you're wrong, you do a quick look around to see where you could have gone wrong. So really nice exam question there. Right, second last example. Prove, so another one of these kind of weird identity ones, prove that sine 7.5 times cos 7.5 times cos 15 is an eighth without the use of a calculator. Now again, the moment I see sine of an angle, cos of an angle, I start thinking double angles. And when I see 15, I notice that double 7.5 is 15. So if I have sine 7.5 times cos 7.5 times cos 15, I want this to be a double angle, which means I'm going to make it 2 sine 7.5 cos 7.5. But if you make it 2, you can't just add that in, so we put a half in front, because then the half and the 2 can cancel each other out. Now you still have multiplied by cos 15 here. So now my half remains there. My 2 sine 7.5 cos 7.5, so my green bracket, this is a double angle, so that actually simplifies to sine double 7.5, which is sine 15. And what do you know? It's another double angle, because sine 15 cos 15 is now a double angle. So this is going to be a double angle, so I want to write it as 2 sine 15 cos 15, except you can't just suddenly have a 2 in there unless you have a half. So a half to cancel out the fact that you just introduced a 2 because you felt like it, and don't forget that there was already a half. So that half pops down. These two you added in to kind of make your identity work, but so that they cancel each other out. And so finally this becomes a half times a half, which I probably should have simplified to a quarter, and this becomes sine of 30. Now sine of 30 is a half. So you basically get a half times a half times a half, which is an eighth. Now again, you'll notice that this is so similar to the previous examples. They all kind of center around the same ideas. Okay, our last example for this video says, example 9, prove that cos 2 alpha plus sine squared alpha equals cos squared alpha. Now this is where we're going to. We're going into trig identities. And so this is just a kind of an intro into where we are heading towards. So my left-hand side says cos 2 alpha plus sine squared alpha, and my right-hand side says cos squared alpha. Now, the thing with double angles and cos is you have to ask yourself, what version do you want to add in there? Now, I need this sine squared to disappear because on the right-hand side there is no sine squared, which means immediately I think I need to at least use the mixture, if not just the sine squared version, the 1 minus 2 sine squared. Now, if I use the 1 minus 2 sine squared, then I'll have no cos squareds, which I want in the right-hand side. And so, taking that all into account, personally, I would use the mixture here. So, cos of 2a is cos squared, alpha minus sine squared alpha plus sine squared alpha. And what do you know? Those sine squareds cancel, and so you go straight to cos squared alpha. So that was just a bit of an introductory question to where we're going in terms of trig identities, which is next. So that's the end of this. These were just 9 examples. We'll start to recognize things quite quickly. 15, 7.5, 22.5. You start to pick up the trend.